I'm going to close that. And let's open up G-Power. Do I have it open down there? I don't. So G-Power is a very nice, very simple um, program that allows you to test a lot of different types of power. We can work out power by hand using t-tests because it's very simple and we just have two distributions. But as soon as we start getting anything more complex, it becomes harder to do. So let's start though with a t-test, which is simple. G-Power has a bunch of different types of tests. You can do an exact test, um, which allows you to do like multiple linear regression or kind of proportions. Um, you can do f-tests, which is ANOVA and COVA. They have a generic f-test down here, variance of two samples. We'll come back to those because we're going to do some of those. You can do t-tests. Usually those are just like mean differences, right? Chi-squared tests, where you can look at goodness of fit, variance differences, and then of course the z-tests. And z-tests are probably the easiest type of test to calculate power. But one of the wonderful things about G-Power is it allows you to compute effect sizes within kind of this framework. We're going to change this to 0.8. Actually, let's go to a t-test. I'm sorry. We will look at this. And you can hover over effect sizes and it will give you kind of the different conventions for the effect sizes that you're looking at. You can also hit determine and it will allow you to plug in different types of, like here's your mean, your standard deviation. And obviously like the difference here is 1 divided by 0.5. That is a Cohen's d of 0.5, right? Like Cohen's d is mean 1 minus mean 2 divided by pooled standard deviation. In this case, you have 1 minus 0 divided by 0.5, which is 0.5. So anyway, you can calculate it, then you can transfer it to your main window or whatever. Let's put this back to point. Let's put this at 0.1. Alpha of 0.05, power here. Allocation ratio of N2 to N1. This means the number of people in group 2 versus group 1. You can adjust this if you have like if there are a different number of people in group 2 than group 1, you can correct for that, right? 1-to-1 ratio means that you've got like 30 people in one group, 30 people in the other. Or that you will have 30 people in one group and 30 people in the other. And our power of 0.8, and then we hit calculate. And it's very nice. It shows you like your two different distributions here. Here is your alpha level. This is your beta level. The probability that the findings from this group, right, overlap with this group over here. And so if your effect size is 0.1, you see that the sample that you need is pretty high, and that's for each group. You need 2,400 people. If we change this to be equivalent, then it doubles, right? So just going from 0.8 to 0.95 requires twice the amount of people, and this is why we say why we are able, or we're willing to do a beta of 0.8 or of 0.2 rather than 0.05. Let's put this back to 0.8, and then we can also change our effect size. Let's say that our effect size is 0.3, and what you'll see here is a change. Oh, I have two things here. A change in like your critical t value up here, and by increasing the power even a small amount, you see a dramatic reduction here, right? Now the problem is we're almost never just doing a simple z-test or a simple t-test. We're almost always doing a more complex model, and we're interested in the power that we have to detect an indirect effect or associations with indirect effects, right? And when you go to write your thesis proposals or dissertation proposals, you're going to specify. So actually, you might just do a regression model, right? So let's do this. And let's say that you are doing a regression analysis, and I don't know about the rest of you. I do a lot of alcohol research, and basically the best predictors that I have for predicting alcohol-related problems usually account for maybe 10% of the variance in something, right? And that's a lot in my world. That means that we have 90% residual or error variance. And it's funny. This is an aside, but I went to a talk one time where a person was talking about the fact that they only predict, like 5 or 6% of the variance, and then he was like, but one person's residual variance is another person's career, right? Like everybody's trying to combine to come up with this 1%, or I mean 100%. But anyway, if we know that you should never plan the statistical portion of your study before you plan the methodological portion of your study, right? You decide what you're going to do and how you're going to test it, and then you sit down and you look at what's the best analytical framework for what I want to do, right? And so let's say that you decide that you want to do, somebody throw me something here that would be just a basic kind of regression-based study, something that you guys are interested in, and let's walk through it a little bit. Anyone? Okay, the relationship between sleep and test performance, that's a good one. And so you're going to have some covariates in there, right? Like you might have gender, you might have age, you might have some other thing. And so the question is, what percentage of the variance, or what proportion of the variance above the covariates is going to be accounted for by sleep, right? And it's sleep predicting test performance, right? I mean, I'm an anxious person, so I would probably say test performance predicts sleep for me. But that's after the test, right? After the test, I can't sleep. No, anyway, so we're going to look at sleep performance, test performance predicting sleep. We know that this is going to be a regression unless we're randomly assigning people to get more sleep, less sleep, whatever, right? In which case, can you use regression for that if you have assigned people to different conditions? Can you use regression? Do you have to use ANOVA for that? Someone say it. Please say it. What? They're the same damn thing. That's right. They're the same thing. Anything that you can do in ANOVA, you can do in regression, and you can do it better. I love ARM2 when I break that down and show you that everything that you can do in ANOVA, you can do in regression better, and show you how you can simultaneously do all of your post hoc tests and regression without having to worry then about doing multiple comparisons afterwards. But it doesn't matter. Regardless, we're going to use regression, linear multiple regression, fixed model, R-squared deviation from 0, or you can use R-squared increase. For this one, let's just do R-squared increase because there's an assumption that we have a number of predictors. If we float over Cohen's effect sizes here, we'll see we have 0.02, 0.15, 0.35. There is a very simple way to look at the relationship between all of these different effect sizes, and I think do I have it pulled up? I don't think I have it pulled up. Hold on just a second here. Let's hop over and open up this effect size thing that I posted for you guys. So you'll notice that I shared this in web courses. Some of my ARM3 resources here. Oh, I bet it's just in this box. It's completely disorganized. There's an effect size calculator, and so you can calculate effect sizes right here, and this will give you kind of Cohen's d sorts of effect sizes. Or you can come down here and plug in effect sizes, and it will give you different types of effect sizes based on various things. So R versus Cohen's d. I have another one that I will share with you guys that I like a little bit more than this one. I thought that that was the one that I actually shared, but apparently not. Let me look here and see if I have. This is the one that I like. This one will convert effect sizes to. Did it open? Oh, it opened way down here. That's weird. I'll add this one for you guys as well. You can input a Cohen's d, and it will give you the equivalent effect size in correlation, odds ratio, f, eta squared, and area under the curve. So, and this is Cohen's f. This is made by Jamie DeCoster. I think it's just such a cool kind of tool. But anyway, I will post that for you guys so that you can have a look at it. We will go with, so this is Cohen's f. So if we put in a value of d of 0.2, actually let's change this to f of, and this is an f of 0.15, but that's an f squared. It's not actual f. So if we were to square this, it would be 0.04. Let's put 0.4, which would give us a Cohen's, or I mean, a Cohen's d of 0.8. That's a huge, huge effect. Let's not use that. 0.1. All right, doesn't matter. I mean, let's just assume that we're going to figure this out based on r squared. So if we wanted to know the r squared or the association that between sleep and test performance, where would we find that data for power analysis, Colleen? What do you think? Yeah, from the literature. Is this something that you're interested in, research-wise?
Sure.
That sounds like a no. I mean, the reason that I'm asking is because I want to know, like, what is the typical relationship between sleep and test performance?
I don't study it.
Oh, you don't?
No, I just came up with it.
Oh, you just threw something out there. Somebody give me something that they're actually interested in so that we have a little bit of a knowledge base. Okay, I'll give you something that I'm interested in. The relationship between alcohol use and alcohol-related consequences. Usually,
I'll give you one just so we're not doing anything with alcohol.
That sounds great.
Competitive psychological climate and job stress.
Competitive psychological climate and job stress. Perfect. What is the correlation between competitive psychological climate and job stress?
Probably like 0.25.
0.25. Okay. And so what is the r squared of that relationship? And is that controlling for everything else?
I believe so.
Okay, 0.25. What's the r squared of 0.25? 0.06? That sounds pretty close, right? So let's go 0.06 is our r squared. We're going to calculate and transfer that to the main window. That's a Cohen's f effect size of 0.0638, which is it's small, but it's between small and moderate, right? Alpha of 0.8. So number of tested predictors, we're just looking at one, right? And let's say that we have 5 other predictors in the model that are accounting for other proportions of that variance, right? Maybe it's covariates or something along those lines, but we're really interested in this one predictor. And what G-Power is doing here is saying, like, okay, this one predictor has an effect size of this. If you put 2 predictors in here, it's going to have an effect size of this. Well, what the relationship between these two things is whatever you put in this box for the number of tested predictors is what G-Power is going to assume is the R squared for those combined predictors. With 1, it's nice and easy. We hit calculate, and it tells us that our total sample size is going to be 125, and it gives us our power and our critical value and all of this other stuff. So if you want to look at the relationship between job, tell me again what you said, job stress?
It's competitive psychological climate and job stress.
Competitive.
But actually, the correlation is only 0.13.
0.13.
Yeah.
What is our R squared of that?
Point oh two.
0.02. Okay. This is more consistent with the type of R squares that I'm usually working with. That is a much smaller effect size. All of these things look consistent still, right? We hit calculate, and that tells us that we're going to need 387 people in order to find that, in order to ensure that if we find a statistically significant, or that we don't miss a statistically significant effect, right? So a lot of, yeah, go ahead, Colin.
Oh, you can finish what you're saying.
Yeah, so a lot of the discussion around statistical power has been one of the things that people will say quite frequently is we found a statistically significant effect and our sample size was very small, but given that we found an effect, we can conclude that we weren't underpowered. There's a real flaw in that argument. What is the flaw?
You didn't detect the bigger effect?
Okay, so that could be, right? That could be the argument, but there's a more important argument here. And that is that with a small sample size, you have a wider variability, and consequently, research has shown time and again that even with a small sample size, you're actually more likely to detect, when you detect a significant effect, it's more likely to be extremely robust, right? In other words, small sample sizes overestimate the magnitude of an effect when you find a statistically significant effect. So to say like, oh, we found this effect even though our sample size was small, so obviously we weren't underpowered, is an error, because in truth, the significant effect that you find with low power is almost always more robust than what you would find with adequate power or with a fully powered study.
Is that because of standard errors?
It's absolutely because of standard error. Yep. And so, anyway, this has been why psychology has gotten ourselves into such a mess, especially social psychology, because they do these experiments with 10 or 15 people, right? And they run them 30 times. And you find one of those that works out of, I mean, theoretically, out of 20 times, one of them should work by pure chance, right? And when that one works by pure chance, the magnitude of that effect is going to be larger because of standard error, broader differences in means, right? Of course, you also have broader differences in variability, but broader differences in means. So statistical power is important not only because it can lead to a waste of time and a waste of resources and a waste of everything else, which is the main argument that people like to use, but more importantly, it's important because it can also lead to more robust effects when you have a type 1 error. That doesn't necessarily mean that low statistical power will increase the likelihood of a type 1 error, but it does mean that if you have a type 1 error, you find larger effects for that type 1 error, right? Anyway, this is the sample size that you are going to need in order to ensure that you don't have a type 2 error when you're testing this sort of relationship. Yeah, Colin, go ahead.
So number of tested predictors is how many you're including in your model.
Yeah.
But then why does the total number of predictors if you're not including them matter?
I'm sorry?
Like the one under it, total number of predictors, if you're not including them in your model.
Oh, no. I'm sorry. There's a correction here for there's a correction in the total sample size for the total number of predictors, but the only thing that power is calculated based on is this in relation to this, right? So if you change this right here to 10, you still get 387, right? If you change this to 10, actually yeah, you get this dramatic difference because it's spreading this across 10 predictors, right? And so consequently, none of these predictors are, I'm sorry, no one of these predictors are very powerful, and consequently, you need a lot more people in order to account for the fact that this variance is coming from 10 predictors versus, or this explained variance is coming from 10 predictors versus one. Here you have one very powerful predictor, right? Here you have 10 very mediocre predictors. And in order to detect significant effects across all of those, you need to have more people. Does that make sense?
Yeah. What does that total number of predictors change then?
It really doesn't change anything. I mean, I don't even know if they use it as part of the calculation, to be honest. I wish I had a better answer for you.
No, that's good. Thank you.
But yeah. Okay. Any questions on G-Power? There's a link to go and download G-Power if you want to. I think this is actually an older version. But let's shift gears to the more important thing here, which is if you download the thing for today, the example for today, you will see
Where is that?
it should be in like readings for this week, I think is where I just put everything in readings for this week. And I'm going to walk you through kind of how I do one of these power analyses.
So are we clicking M plus power analysis or just M plus?
What is it? I don't remember what it says. What does it say in there? Can somebody tell me?
For the file name,
Yeah.
it's n plus power example.imp.
Yeah, that's what you want. It doesn't, mine might look a little bit different. I think I went in and made some slight changes. And I'll walk you through why I made the changes that I made. And you guys can make those changes on your own as we do this. So the first thing that you want to do before you do a power analysis or anything is you want to draw it out, right? And so we have this model that I want to do a power analysis for. Do I have X3? I do. This is our basic model, right? And so we need to know some things for this model. What do we need to know in order to do a power analysis? What we want to know is if the indirect associations between x1, x2, and x3 on y1 and y2 through m are what sample size we need in order to ensure that we do not have a type 2 error, right? That we don't miss this indirect effect. So what do we need to know? Also, power analysis is about 80% art and finesse and about 20% BS. Yeah.
So what do we need to know to determine the sample size?
Yeah.
So the alpha and the beta.
Okay, so we already know those, right? Those are kind of set. If we have a model like this, and we want to collect data on this, and we want to know like what sample size we need, what do we need to know about this model?
What tests?
Okay, so we need to kind of generally know, based on the literature, what this relationship here is, right? We need to generally know what this relationship here is and what this relationship here is. Now, technically, if you have those things, you could run through and you could do like, okay, so I'm going to do a power analysis for this, and I'm going to do a power analysis for this, and a power analysis for this, or a regression analysis that includes these three predictors with the cumulative R squared, right? But the problem is, you'd also have to do one for this piece and one for this piece, right? And then you've got to try and figure out a way to logically examine this relationship through here, having done multiple different power analyses already, right? In M+, you can do it all at once. You can run a single model that has all of these things input into it and test the extent to which you, or the number of people that you need in order to ensure that you have the requisite sample size to not miss that effect if it's there. So let's look at what we've got here. And this is going to be a little bit different than what you guys have. I'm going to start from the top and I'm going to walk through and I'll give you kind of the rationale for it. So we have our parameters that I already drew out on the board here, right? Oh, and just FYI, for the homework this week, I will give you guys a figure. I think I probably should have given you a figure for this past homework, right? That would have made it much easier. I've done that in the past for, I think for ARM. Did I give you guys figures in ARM 2 to use? I've done it in ARM 3 in the past. So I will give you a figure for this week and say like, here are the basic relationships. I want you to conduct a power analysis and let me know like, and then actually for this week, maybe you don't even need to submit any type of write-up. Just submit your power analysis and how you determined how many people were going to be required for this study. Something that you should also think about, and this varies based on your area of study and so on. If you're doing an experiment, you don't have to worry about this. If you're collecting data through the SONA system, you do have to worry about this. Missing data, which we're not going to go through today, but more importantly is attrition, right? Just people dropping out. So if you're if M+ says that your power will be X with a sample size of Y, you should plan on having a certain proportion of attrition. I do college student drinking. My attrition I usually assume to be about 20%, right? So I always plan on collecting about 20% more than what I will actually need. Anyway, here's our variable names. N observations is the number of people. In contrast to G power, where it tells you how many people you have, M+ requires you to put in the number of people, and it will calculate the power based on the number of people that you put in. We'll toy around with that a little bit here in just a second. Repetitions, the way that this works is it's a simulation. That means it will run this model over and over and over, and it will build a set of distributions for every parameter, and you'll get a average effect and the standard error of that effect, both in the population and in your predicted sample. Seed is just telling M+ where to start the random seed for this kind of walk that it's going to do. You can put any number in there, or you can omit it completely. I just throw in some random numbers. If you omit it completely, M+ will use the current time of your computer to seed it. If you ensure that you always put the same seed, then you will ensure that M+ always starts a walk at the same location, and you will get, like you can go back and rerun this exact same power analysis and get the exact same results, right? Okay. M plus requires you to put in your model population. This is where you're telling M plus, these are the effects that we have, that we assume are true based on the population, the larger literature that we've got. Some of this is also required in the model, some of it's not. These do not have to be exactly the same, and we'll get to why I want you to think about why your model population and your model might be different. We'll talk about that in a second. So this is not a recommendation of M plus or anyone else. This is a recommendation of me. You'll note right here, I do a few things. When you put something in brackets like this, and then you put at, does anyone know what that tells M plus? Brackets indicate something very, very specific in M plus. Brackets tell M plus this is what the mean is. We're going to fix this mean. And so what I'm saying here is x1 through x3, x1, x2, x3 has a mean of 0. And then right below it I have x1 through x3 at 1. What is M plus doing there? Anybody know? That's fixing the standard deviation of x1, x2, and x3 to 1. So if x1, x2, and x3 have a mean of 0 and a standard deviation of 1, those are what? Standardized, right? These are standardized, and that the reason that we do that is because we're going to have to eventually start specifying relationships between variables. And the easiest way to do that, in my mind, is to put a correlation, a standardized relationship. So if you standardize the distribution and the mean of your variables, then your standardized coefficient, the coefficient that you put in there, is a correlation. And it's easy. If you don't do that, then 0.3 means for every one change in x, there is a 0.3 change in y or whatever. And you can work off of that, but the effect sizes are more difficult to understand. Correlation is an easy to understand effect size, right? Okay. I do the same thing with M. I fix this to 0, and I fix the standard deviation to 1. And with Y, fix them to 0 and the standard deviation of 1. And that puts everything on a standardized scale, right? It makes everything a z-score. You don't, because I added this stuff. Sorry. Yeah, you guys can go ahead and add it now if you want. It's also going to be in the video, so it's up to you. I know that when I initially uploaded this, I don't think I had put M or Y in as standardized yet, right? And in fact, later on down the thing, I might have put like 1, 2, and 3 as like the means for Y. I don't remember. I know that I was toying around with this a little bit when I was planning to talk about it today. Then we start to specify our model, right? And in this one, I specify both the relationships between x and y, and y1 and x, all of the x's and y2, the mediator, and then the mediator and x1 and x2. Oh, I don't have x3 in here. Huh. Let's add it. x3 at 0.4. And I'm going to have to throw that down here too. Okay, so all of these are specified as fixed parameters. This star, asterisk, whatever you want to call it, is something different. Anybody want to take a guess at what that asterisk is saying? Yep. Yeah, and it's the average relationship, right? We're going to say like the average relationship between these variables is this, and that doesn't necessarily mean that that's what it always is, right? And M plus will calculate a distribution. Like these ones up here, these are going to be fixed. M plus will never change the standard deviation or the variance or the mean of those when you use at. When you put a star, M plus says, okay, so the mean should be near this, right? And it's going to start with these Monte Carlo simulations, assuming that this is the average and that there's some variation around that average. And so we set these based on what? Where do we come up with these numbers? Yeah, correlations from the literature, absolutely. And every one of these is a correlation. And of course, some of these are ridiculously high, like 0.5 and 0.4. Similarly, down here, we have these correlations that come from the literature, and those are the relationships between M and X. And then we have this here. We have no ons or anything. Anybody want to take a guess at what that might be? Yeah, it's residual variances, actually. It's the residual variance for y1, y2, and m. The average residual variance across draws should be roughly 0.9. What does that mean? It means only 10% of the variance in y1, y2, and m are going to be explained by our model, right? And so if I were to say like 10% of your variance in your mediator is explained by your predictor variables, and by the way, these don't have to correspond with what's going on up here, right? Because we're talking about averages. But if we say 10% of your variance should be explained by this, then you'll know that, okay, then I need to specify residual variances down here, right? And actually, I did have the means. I remember earlier I said, oh, I think I had specified means. I did. Okay, down here in model, we don't need to go back and say like, hey, these are fixed variables. This is the mean. This is the variance. We've specified that in model population. We said in the population, here is the range of these potential values. Now we're just going to look at our model. Consistent with almost every type of power analysis, if you're doing an a priori power analysis, you're assuming that your model is going to map onto the population, right? In which case, the model that you specify should match the model in your population. However, sometimes they don't, and sometimes we don't want them to. What type of power analysis would we be doing if we assumed that the latter there? Anybody want to, what's that? Okay. So we could do, sometimes we run a study, things don't work out, right? And we've run a power analysis ahead of time, and we've come up with a sample size, and then we want to understand why in the world did this not work out. You can go back and specify, here's what the population says this model should look like, and here's what my model actually looks like, right? And you can rerun your power analysis based on what the population is relative to what you found, and that will give you the power of your current sample relative to the population, right? And so you're able to parse that out and say like, oh, okay, so I actually thought that I had enough power, but I didn't. Or you might be able to say like, okay, so actually this is powered, so it's significantly powered, but my effects just don't match up with what the population has. So either the true effects in the literature are not correct, or I have a type 2 error and the true effect is not there, right? So, yeah.
Like there might be an issue that I have some exogenous variables in my experiment.
Yeah. So when you say,
with some other factors impacting my sample.
yeah.
Because we should not let the population, I will reduce some other heterogeneity when I was doing the experiment.
Yeah, I mean, that's a great point, right? You might be able to say like, oh, I've controlled for this piece of this model that is not typically measured in the larger population, and that might have affected my ability to detect a significant effect here. So, sure. Okay, and then in model indirect, we just kind of lay these out here. Also, this is probably not in yours. I don't think I added model indirect to your guys's, right? Oh, it is in there? Okay, good. And I have Tech 9 down there. Don't worry about that for right now. So we run this. It's going to do 1,000 iterations. It'll do it pretty quickly. And it's done. And let's scroll down. Actually, you know what? I'm going to come back. Well, let's just do 20 of these. And then we'll come back and we'll do 1,000. So if we run 20, the first thing that we get is, these are all of the kind of basic statistics that you get with, fit statistics that you get with a normal a normal SEM model, right? And so it gives you the expectant and observed proportions and percentiles of, why does it say 1,000? I thought I changed that. Oh, did I change that to people? Oh, I changed it to 20 people.
That's why mine was different. I had all observed as 1, 1, 1, 1, 1.
Gotcha. I didn't change the actual number of repetitions. I just changed the people. We're gonna skip over that for right now. Let's come down here, and yeah. So proportions of observed to expected is 1s all the way down for this. You had 1s up here as well? Anyway, let's come down to our model because that's the important piece for right now. All right. So this model gives you the population that you've specified. These are the effects that you've specified, right? These are the average estimates based on those 1,000 random draws that we had, right? And we said that we only have 20 people, which winds up being like you get this very wide standard deviation and standard error average. And then this last column over here is our power for each one of those paths that we specified, right? So for x1 on y1, our power is 0.11, x2 on y1, 0.19, 0.14. Note that these are all small effects, right? And if your effects are small and your sample size, what was my sample size? 20. If your effects are small and your sample size is small, you're not going to have very much power, right? And that's exactly what we see. If your effect size is large, even with a small sample size, it's going to suggest that your power is a little bit more. Of course, what do we want this final column to be at? Yeah, we want it to be 0.8 or higher, right? So none of these, we kind of have some x1 on, it's a huge effect size, which is probably completely irrational, but we're less concerned about the intercepts, by the way. If we're fixing this to 0, what this is really saying is like what proportion of the random draws did we find a statistically significant effect over here. And even though we're specifying this as 0, every once in a while, we get a mean that's far enough away from 0 that it's a statistically significant parameter, right? And that's what all of these are. It's how many times do we get a statistically significant parameter. The standard deviation, 100%, or residual variance, 100% of the time is statistically significant because we've got tons of residual variance, right? And then if we come down to our indirect effects, 42% of the time we have a total, and 30% of the time total indirect effect that's statistically significant. And that kind of runs across the board here. Basically, what would you conclude from a power analysis with these types of power, this type of power for each of these effects? Our sample size is way too small, right? Now, in contrast to G-power and some of these other power things where, I think I already said this, where it tells you what sample size you need, M+, you specify the effects, and it will tell you what your power is given the sample size that you've specified. So we have to go back, and we have to plug in a new sample size, right? So let's go back, and let's plug in a sample size of 100. We hit save, we hit run. We come down to our effects. And if we're assuming, based on this model here, that the relationship between x and y is completely mediated by m, does it make sense to assume that these powers are not going to hit 0.8? What do you guys think? What is this column telling us again? Power, which I mean, in layman's terms, what does 0.162 tell us about the relationship between x1 and y1 given 1,000 draws and a sample of 100?
There is a huge time where we are not getting the effects actually, while they are the effects.
So it says 16% of the time, 16.2% of the time, actually, this model showed a statistically significant relationship between x1 and y1, right? That means out of 1,000 times, 162 times, there was a significant relationship there. The vast majority of the time, there was no statistically significant relationship. But every once in a while it happens, right? Because every effect that we have falls in some sort of distribution that varies around 0. And this one strays not very far away from 0, right? For the most part, it's always 0. And then every once in a while, 16% of the time, it's statistically significant. If we have a fully mediated effect, we would expect that, right? We would expect that if we ran this experiment or we ran this study 1,000 times, that 16% of the time we might find a relationship between x1 and y1, but 84% of the time there would be no association because it's fully mediated, right? But statistics means never having to say that we're completely sure about anything, and sometimes it just happens that that relationship is there. Similarly here, that relationship, 46.5% of the time we see that it is statistically significant, and that's because the average relationship, right, tends to be a little bit further away from 0. Here, what does this tell us? Yeah, we got a lot of power, right? Like 99.6% of the time, that means on 996 of these random draws, the relationship between M and Y1 was statistically significant, right? Only 4% of the time it wasn't. That's important though, 4% of the time it wasn't. That means that if you ran the study 1,000 times, at least 4 times, that relationship would be non-significant, and we would then commit what? Type 2 error. Yep, absolutely. Okay, moving down, we see here x1 and y2. We are still kind of underpowered to detect a statistically significant effect here, but again, if it's fully mediated, we don't care. This is the one that we're really concerned about. And then finally, we want to look at all of the relationships between x1 and m. And here, 100% of the time, x1 and m were statistically significant. 1,000 draws, 1,000 significant effects, right? It's a pretty strong relationship. Here, also pretty strong. Only 3 times that it didn't reach it, and here only 17 times that it didn't reach it, right? So for the most part, it looks like we are going to have plenty of power with 100 people to detect a relationship between X and the mediator, and plenty of power to detect a relationship between M and the 2 outcome variables. But that doesn't answer what our initial point was here, which was what? What is our power? We could have done all of that in G-power, right? Every single one of those things we could have done in G-power with the regression model. But what we really wanted to know, the whole point of the simulation was to look at what? The entire model, and specifically those indirect relationships, right? Will we have enough power to detect the indirect relationships? So we scroll down here, and from x1 to y1, here's our power to detect the indirect and total effects. Notice that this total effect, even though it's nothing, right? Or at least we're very underpowered for a direct effect, which we expected. We completely expected that to occur. we do have enough power to detect significant indirect effects here. X2 to Y2, similarly, enough power, we don't worry about this. X3 to Y1, this is important, right? Because we are just powered to detect a significant total effects from X3 to Y1. Now, the indirect effects look solid right here, but if you want to know total effects, and you want to ensure that those total effects, if there are total effects, that they cross that threshold of statistically significant, then we are just powered to detect that with 100 people. What did we do? Was it 100? I can't remember. And the rest of these all look pretty good. This one we're talking about a really, really robust direct effect, which of course translates to 100% coverage up here. Here again, we see this type of relationship, but for the most part, our theory was saying that everything should be completely mediated. And so we can conclude from this what? Yeah, yeah, with 100 people, assuming the effects that we have here, we are well powered. We could go back and we could change one small thing, right? Let's change. Let's change this to 0.1. M on X1, 0.1. We hit run. We scroll down to look at our power for.
These points are standard error.
It's a correlation. Correlation, yeah, correlation coefficient. And if we were to change the X1 on M, our power is reduced dramatically, right, 0.17. And then if we want to look at our indirect effects, like they're gone, right? How can we fix this? If that's our association, if our effect size is 0.1, what do we do? Yeah, add some people, right? So we had 100. Let's up that to 1,000. Our power was what before? 0.17, I thought, right? So we scroll down here, and X, that jumps our power up to 0.922. Notice that all of the other powers are huge now, right? And so we could say, well, with 1,000 people, we have sufficient power to detect this X1 on M1 relationship. And if we come down to our indirect effects, we are also sufficiently powered there. In fact, we're overpowered a bit. We don't really need 1,000 people, right? And so the take-home message here is that it takes a little bit of toying around with an M+, because you've got to bounce around with that population, right? You've got to bounce around with the sample size until you hit that spot where M+ says, yeah, you are powered. So with this, we might say, okay, so 1,000 is good. Let's see where we're at with 900. Because if we don't have to pay 1,000 people, we don't want to pay 1,000 people, right? Down here, we're going to check first our relationship between X1 and M, 0.9, it's still pretty good. And X1 to Y1, it's still looking pretty solid. 900 is more than what we need. 800.
If you get ones in the power column, is that okay? It's just over.
Oh yeah, it's just like well overpowered. Like 100% of the time, you detected a significant effect. Now we're at 0.85 there, and our indirect effect, or our total indirect effect, is 0.847. This is probably about the spot where I would stop, right? I would say at 800 people, we have this sort of an effect. So, yeah.
Could you use the G-power in 10 with M+ and reduce the trial and error?
I mean, so Yes, I suppose that you could, but G-Power never calculates the indirect effects, right? And so I don't know that it's so much a trial and error. Like this isn't the type of thing where you have to worry about multiple tests, right? Like you're running simulation after simulation to get to a spot that says like, okay, I can be relatively confident at this point that if I recruit these many people, because you're not worried in this, you're not worried about a type 1 error, and that's where multiple tests are a problem, right? Is type 1 error. Here, we're just trying to understand sample size. So, any other questions? So homework for this week is going to be a power analysis, a simulation in M+. I'm going to, actually, you know what? Let's take a break real quick. I just have to go to the bathroom so bad I can barely stand it. We will take a break for like 5 minutes. We'll come back. I'll walk through the homework really quick, and then we'll call it good for the day. Sound good? All right.